Okay, good morning. Close that. So, do I have it here? Maybe not. That's okay. So I made those instructions quite a long time ago. And there were some questions about the instructions, but this is just, I've just extracted it from the textbook. So if there's anything missing or kind of unclear, then maybe I just copied and pasted in a weird way. And then when I ran through it, I knew what I was supposed to do, and then that's kind of a problem. So, but anything in particular that came up here? There were some questions about the geometric mean. So it gets you to do all these things, and some use different data sets, right? Because we've got categorical or numerical data. But if you just put them into different sheets and submit it, then that's good. Or I think you're allowed to submit more than, I think it's 20 files. So if you want to do them separately, that's fine. But I just want to see your final results, right? And it usually tells you what it should look like. There was something. Were you saying the geometric mean?
There's no data set for it.
The mutual fund returns wasn't in there? No. I thought, but that's okay. Okay, so then I'll post it because it's good to have seen it, but it's not there. Oh, dang. Okay, that's okay. I'll make a note and I'll post it. Are there any other questions? I'll highlight this so I remember.
Just for me, it's just some clarity with what exactly it's asking us to do, because it's telling us how to do things, but is that what you want us to, like?
Yeah,
you know what I mean? Like,
it
okay,
is.
I understand, I know how to do this.
Yeah. As long as you can replicate, that's all I want. That's all I want to see. So obviously everyone's getting 100%. There's no reason not to, but I just want to see you work through it and have it,
Well, like,
and
for
have
example,
done it.
with the home sales, right? The conditional formatting, it asks us first to get them highlighted in red for any of the negative values.
Yeah. Oh,
But
and then it
bars,
switches.
But see, I handed mine in without removing the red because it doesn't say to remove it. You know what I mean? Like,
yeah, that's fine. That's fine. As long as you kind of show me that you did all these things, that's totally fine. Yeah. Cool.
All the formatting on all the exams.
Yes. Yeah.
And then submit
the Excel sheets. Yeah. Yeah. And I can extend the due date. I'm not, super particular about due dates in general. So, except for tests, those are important. But that's something that I realized I hadn't said to you guys, but I know you guys have deadlines and everything. And so if you just let me know if you need a due date bumped, totally fine by me. Okay, so it doesn't matter to me. But so if you've got something breathing down your necks, then let me know and we'll change it. And it can be flexible like that. Okay. The only other question, or any other questions about the Excel practice? Kind of like just getting you to do stuff. Okay. Then I'll even do it in red. Emily, that post data. That's a note to myself. Okay, so a little bit of review. Maybe I'll close this door here. We introduced just kind of some different shapes of distributions. And so let's do a tiny bit of review here. We looked at some shapes of distributions. For numerical data especially, well, okay, maybe I should start from the top. We talked about variables. Variables are either numerical, but this textbook calls them quantitative, or categorical. Get myself a little bit. So for the shapes of distributions of numerical variables, we introduce this unimodal symmetric bell-shaped curve, which we call the normal distribution. And then we introduce some other shapes, but let's just focus on unimodal distribution. So one peak, right? And so it can be skewed to the left if we have a tail to the left. It can be skewed to the right if we have a tail to the right, right? And so we can have things that look like this. So this is skewed left, or if you prefer a negative skew, that's fine too. Just remember that it's skewed in the direction of the tail. And then same thing, we can talk about distributions that are skewed to the right, because we've got a tail to the right, skewed right, or a positive skew if you prefer. I'm going to lump these into non-normal distributions. So we'll just kind of generally call these non-normal distributions. We introduced the concept of a bimodal distribution, multimodal distribution. Modes are the number of peaks, right? And so if we're talking about bimodal, then we have two distinct peaks. And but here I said, let's just focus on unimodal distributions, because kind of multimodal distributions usually mean that you've combined two groups that shouldn't have been combined. Right? Or maybe you should analyze them separately. Yeah. So, okay, from the shape determines or dictates rather what the appropriate measure of center is. Okay, and so from the shape, if the shape is normal, then the center, the most appropriate measure of center, is going to be the mean, the average. And for the spread, we haven't introduced the spread yet, but just as a heads up, it's going to be the variance or standard deviation. Maybe I'll bump this up. Whereas if we have a non-normal distribution, then there are a couple of different options for the mean, but generally we would use the median. The median is the central value of the data, right? And we saw that, okay, the mean is affected by outliers, so extreme values, whereas the median is not, right? And so for the spread, we usually use the interquartile range. Oops. Which we haven't introduced the spreads, but we will today, hopefully. So the shape of the distribution determines what we should be using as the center and the spread. we ended on the geometric distribution. Dun, 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 dun. Where is it? Or the sample, the geometric mean. And I said off the top of my head, I can't remember when we use it, but I should have just trusted my gut. We use the geometric mean, which is similar to the arithmetic mean, which is where we add them all up and divide by n. That's the mean that we're used to seeing. A geometric mean is if you have kind of non-independent values, right? So stock prices from day to day to day to day, right? Those are not independent of each other. And so then we would consider the geometric mean, but it's pretty rare. Right, so here the geometric mean is used when values of x are not independent, such as stock prices, right? Or I should say daily stock prices. Daily temperatures, right? The temperature today depends on the temperature yesterday, that kind of thing, right? And so daily temperatures. But it is pretty rare that we use it. Rarely used, at least in my experience. What's the difference? Instead of adding things up, we're multiplying things and then taking the nth root instead of dividing by, so adding things up and divided by n, now we're multiplying n things together and we're taking the nth root, right? And that's the difference. But Excel will just do it for you. Okay. Feel like I said some other stuff, but it was last week, so who knows? Anything else that I need today? It's like a previously on. We talked about, yeah, centers. Oh yeah. One last thing. We use the mean, right? Or I should say, maybe I'll flip it. We use the median for non-normal data. Because the mean is pulled in the direction of outliers. Because the mean is pulled towards outliers. Kind of extreme values. Could have more than one, so I'll just put the outliers in brackets. Okay. So in terms of describing a distribution, I'll call this the end of our review. To describe a distribution, we need to talk about three things. We need to talk about the shape, we need to talk about the center, which we've already talked about, and we need to talk about the spread. So to describe a distribution, we need to discuss three things. We need to talk about the shape. And for us, I'm happy with just focusing on, is it normal or is it non-normal, right? I'd love it if we could specify skewed to the left, skewed to the right. That's kind of the, chapter 2 stuff. But in general, we're just going to lump them into normal or non-normal, right? So normal versus non-normal. The center, right, is going to be, now, if you're just looking at a distribution, then you just eyeball it. Where would the center be, right? And it would be kind of with the lump of the data, whether it's normal, so then it's in the center, or if it's non-normal, it would be with the bulk of the data, right? And you're not kind of swayed by those outliers so much because you'll be using the median. So the center is either the mean versus the median. And so the spread, oops. Which we're introducing today, right? The final thing that we need to be able to describe a distribution. The spread for a normal distribution, we said, should be the standard deviation, but it's really just the the variability in the data. No? So, where is it? Measures of variability. Kind of a fun or interesting example, I guess. So we've talked about the measures of location, which I'm calling center because I feel like it highlights it better. But we want to talk about the variability or the dispersion, but I'll call it variability usually. So for example, if you have some two financial funds and they both require $1,000, so same buy-in, okay? And fund A, fund A pays out exactly $1,100, so you make $100 each year, whereas fund B has many different payouts, okay? But the mean, so the average is still 1,100, right? So on average, you're expecting $100, right? If we look at the graph of this, what we mean is something like this. Copy. Right. And I think if I just gave you this to look at, and I asked you which one has the least variability, just intuitively, you would say, well, this one doesn't seem to have any variability at all. And that's exactly right. Right? Whereas this one, right, had different payouts, different years, right? And different frequencies. And so here, no variability because it always pays out. You always get $100. Whereas this one here, the spread, oops, is the variability. Now, there are lots of ways to measure variability, but a lot of them hinge on the distance from the mean. Right? So we talk about deviations from the mean. And so each data point is going to be some distance from the mean, which we can then talk about in terms of, oh, I guess I forgot about the range. It's hardly worth mentioning. We don't really use the range. Of course, the range is a measure of variability, but there's not much that you can do about the range. The range is the distance between the maximum and the minimum, and that's it. So of course, it is something, but we don't really use it. I was amping up to the variance. Let's do this. Copy. So the variance is based on the deviation about the mean. So what we do is we take the distance of each observation from the mean, right? That tells us how spread out things are around the mean, right? And then what do we do? So then we have a list of deviations, but then if I try to add those up, right, I try to get some measure of spread, what happens? I've got negative values, I've got positive values because the mean is at the center. And so then they add up to 0, and that's just a fact. So what do you have to do? You have to square these values, or one of the things that we can do, the most common thing that we do is we square the values, right? Squaring a negative value generates a positive, but also it has that property of amplifying larger distances, right? And so we're kind of penalized for larger deviations. Okay? And so these here, how can I? So xi minus x bar, recall x bar is the sample mean of x. So x bar is the sum of the x's over n. Now what this xi minus x bar says is if I have a data set called, or a variable called x, then I'm going to have x1, x2, x3, all the way down to xn. So from each of these, I can subtract the mean, right, to find the deviation from the mean. So you find the deviation. So maybe, which is going to be x1 minus x bar, whatever it is, x2 minus x bar, x3 minus x bar, xn minus x bar. Put brackets around that. So this part of the formula for the variance, right, you still have that same length of your data. You still have the same number of observations, but now you have that number of deviations. And so then what we have to do is we need to square the deviations. Oh gosh. Then we square the deviations. Couple of reasons, right? Squaring makes things, negative things positive, right? So negatives squared are positive values. Which makes sense. Otherwise, you run the risk of having a negative spread, which doesn't make sense, right? You either have 0 spread, right? Like we saw where everything is the same, all the data values are the same, and there's no spread at all, or you have some positive spread. You can't have some negative spread. Okay? And so negatives squared are positive values. And I'll add, we can't have negative spread. But also the second point is that large deviations are amplified. Things like, so if you have a deviation of 1 or 2, right, I've increased by 1, then the deviation squared, if we think about it, deviation squared, 1 squared is 1, but 2 squared is 4. So now an increase of 1 in the deviations is an increase of 3 in the squared deviations, and that's what we mean by amplifying those larger deviations. Then what can we do? So we tackled the negative deviations, we squared them, we made them positive, right? And then what we do is we add those all up, right? So this sum here tells us that we're going to add these all up. So if I just write out S squared, which is the variance, and maybe I'll specify the sample variance. Is S squared. S squared is the sum of xi minus x bar squared over n minus 1. Yeah. So then here, maybe I'll use green. Add up all the squared deviations. And then finally, you're going to divide by n minus 1. Divide the sum by n minus 1. Now, a quick note here, we use n minus 1 because it's a sample and it just gives us a better estimate. We don't need to worry about why it's not n. I think we kind of would want it to be n, but there's a lot of hand-wavy theory behind it. And we get a better estimate of the variance if we use n minus 1. Remember, we've got the sample variance that we're trying to mimic the population variance, right? We want a little mini version of the population variance. And so that's what I mean by a better estimate, is an estimate closer to the population variance. And so let's see here. I'll just add n minus 1 gives a better estimate of the population variance than dividing by n does. So we have this scenario where we're trying to use a sample variance, but we're trying to mimic the population variance. And so we have all these terms where we have kind of the big brother population situation, but then we have our sample that we can calculate things with and just find information about our sample, right? So we're going to have, we only do calculations on a sample, right? But we're trying to learn about the population. But we're trying to learn about the population. So what we're going to have is we're going to, for example, use a sample mean, but what are we really trying to learn about? We're trying to learn about the population mean, right? Which means that, okay, I need some notation to keep those two straight. And so I feel like I introduced it already, but who knows? Sample information or a measurement from the sample. Let me write that up. Doesn't hurt. A measurement from a sample is called a statistic. Notice sample and statistic. While a measurement from a population is called a parameter. P and P. So for all these measurements that we can make on our sample, we're going to have population equivalents, so parameter equivalents. And so we've got the statistic and the parameter version. And so far, we've introduced things like the mean, where the statistic is denoted by X bar, right? The sample mean of X, we denote it by X bar, or anything with a bar over it is a mean, a sample mean, whereas the parameters, so the population mean, is denoted by the Greek letter mu. So this, can't remember if I had time to introduce it or not. I got one hit. Now I have. Okay, so we've got this sample information, but we're trying to learn about the population mean, which we need some other notation for. And so in general, we're going to use Greek letters. Greek letters denote parameters. They're not something that you're going to be able to calculate, but we are able to calculate statistics, right? Things from samples. But the goal is to be able to take sample information to learn about what the population looks like. And so the next thing we saw, well, most commonly, is the variance. And we introduced the variance as having the notation as a lowercase s squared. Now the variance for the parameter is going to be denoted by a sigma squared, a lowercase sigma squared. So it's a little O with a tail on it. And I feel like you've seen Greek letters, somewhat measurements and things like that. Maybe not. Yeah, definitely in physics. I'm thinking in water, you guys have micros and things, maybe different contexts, but this is a sigma, a lowercase sigma. And so one of the trickiest parts when we first start learning about this stuff is keeping track of, okay, what is the statistic? So what's the sample information versus what is the parameter? So what am I trying to learn about, right? Because I use a sample mean to try to learn about the population mean. Right? So as long as you keep that in mind, then it'll be a little bit easier, maybe. Okay. So we'll have these relationships, right, where we have some sample version that we're able to calculate, but ultimately we're trying to use it as our best guess for what the population version is. So the next thing would be the standard deviation. Oops, little curve. Now, the standard deviation is just the square root of the variance. And so once you have the variance, you can take the square root of it. It's the positive square root of the variance. And so then the standard deviation S, oops, is just denoted by S. And once you take the square root of sigma squared, you have sigma. So the standard deviation is the positive square root of the variance. So then the standard deviation is the square root of the variance, which means that the square root of s squared, for example, which is just s, the positive square root. So when we're writing about the standard deviation, usually we use an SD, whereas the notation in a calculation, we use a lowercase s. And so shorthand in writing is SD versus the notation used in calculations is a lowercase s. Good. Let's see here. Put it in here. And there are tiny little notes about the population, but you're never going to calculate anything about the population, because if you have the population, right, if you have information about the population, then what's the point of taking a sample of that population and trying to figure out what the population looks like, right? Which is what we're going to be doing, right? And so if you have the population, then you're done. You can draw firm conclusions about the population and know everything about it. So we only calculate, I think I said it earlier, but doesn't hurt. We will only calculate statistics, since we will never have the population information. So usually what happens is, as we're starting out, we use the standard deviation as our measure of spread, like I highlighted in the beginning. But then what happens as you progress through statistics, then you start using the variance. But the reason that we don't use the variance right away is because the units are squared, which makes it harder to kind of wrap our heads around. And so we will use the standard deviation rather than the variance. And there are a couple of reasons, but one of the reasons is the variance, the units are squared, is for the variance, the units are squared. Right, which can get complicated. For example, if we're talking about if X is a measure, X is, well, okay. No harm, no foul, I guess. If X is measured in meters, right, then the variance is in meters squared, right? Versus if you take the square root of that, then of course, then the units are back to meters, which is easier to think about because you have an average in meters and then you've got the spread in meters. And so it's just a little bit easier versus the standard deviation is in meters. Let me, hello? Hello? I feel like it was on here. Nope. False alarm, maybe. So that's why we're going to use the standard deviation just in general. But then later, I don't know why they make the switch, but later in courses in statistics, you would use the variance. But they're the same because one's the square root, and that's it. Okay. Notice that we're focusing on numerical variables, right? Because categorical variables, we don't really talk about the spread of categorical variables because we just have counts in each category, right? And so there's not a lot to do there. Okay. We can also talk about, this one's not as common, but we could talk about the coefficient of variation. Okay. Now the coefficient of variation is, it indicates how large the standard deviation is relative to the mean. Now, this isn't something that we're concerned about, but usually what you want to make sure is that your standard deviation isn't larger than the mean. And so usually we just ignore that, but it is something, because what does that mean? It means your spread is larger than your center, right? And so then you've got this huge spread. And so I only introduce it because the calculation is relatively simple, right? If you have the standard deviation and you have the mean, you can take the standard deviation divided by the mean, and then it's reported as a percentage, right? And so that's easy enough to do, okay? But we won't be using it. We won't use this much. Okay. So where we started today, we said, okay, if I have a normal distribution, then I'm going to use my standard deviation as my measure of spread. Now, what if I have a non-normal distribution? Then I've got options. We can talk about percentiles. Copy. Oh, it's fine. Maybe this doesn't need to be so big. Percentiles, you can use percentiles for any data, whether it's normal, non-normal, okay? It just says at this point, I've got P% below this point and 100 minus P% above this point, right? And so percentiles can be used for normal and non-normal data. One of the tricky things, I should say data, is that there's no built-in mechanism in Excel or any other software for that matter that says, oh, I shouldn't be using the mean here, right? So we know that if I have a non-normal distribution, then I shouldn't use the mean because the mean is pulled in the direction of the tail, right? And so we know that, right? But there's no built-in mechanism that says, whoa, I probably shouldn't use the mean here, right? And so we'll always be able to calculate all these things. We'll always be able to calculate the mean, the median, the standard deviation, the percentiles, later the quartiles, right? And so we'll always be able to calculate these. And so it's our job to know which ones are appropriate, right? Depending on the shape. So percentiles are often reported in kind of newspapers and not necessarily journals. but just kind of regular life stuff. The Pth percentile tells us the point where we have P% below and 100 minus P% above. Now, if I have a normal distribution or any distribution really, but my go-to is a normal, right? What I'm gonna have is I'm gonna have some area under the curve, right? Because that represents my data, right? I've got bars of data. And so then if I talk about some percentage below some point, right? I'm forcing this to be P%. And then this point here is the percentile, the Pth percentile. Okay? So the value that separates the lowest P% from the upper 100 minus P%. So here you've got 100 minus P%. Which means what? It means you're going to have 100% underneath the curve in total, right? But one of the biggest mistakes that people make is you say, oh, I scored in you wrote your SATs or I don't know, whatever the provincials are these days. You scored in the 5th percentile. What does that mean? Sounds good, but you don't want to be there, right? What does that mean? It means that 5% of scores were below yours, and then 95% of scores were above yours. That's bad. You want to be where? You want to be in the 90th percentile, the 95th percentile, right? So just in terms of terminology and how you use the word percentile, because it's kind of counterintuitive, I think. Now we're going to use Excel to find the percentiles, right? But there are formulas that you can use. This tells you the location of the Pth percentile, right? So you want to have, you have your sample of size n. You do n plus 1 because otherwise it kind of gets bumped around. And then you multiply it by P over 100, saying, oh, I want this cutoff point of n. So that's just the location. And so that's important. Then you still have to find it, right, in your sorted data. But we will use Excel to find percentiles. So that's fine. So you don't need to worry about the location of it or anything like that. Just know that it's the value that splits the lower P% from the upper 100 minus P%. Now, the reason we really introduce percentiles, well, yeah, it's good to have, but also is because we're going to be talking about quartiles. Now, quartiles are special cases of percentiles. So quartiles are special cases of percentiles. Quartiles got reaction. So you've got your data, set. What could you do? You could sort it from smallest to largest, right? And then we could split it in half. We found the median that way, right? The point that separates the lower half from the upper half. So what does that mean? It means the median is the 50th percentile, right? So we already found a percentile earlier when we were talking about the median. Right? And so the median is the 50th percentile, but we also call it the second quartile, right? Because we can split our data into quarters. And so the first quartile is the 25th percentile, right? So you've got your data, sorted from smallest to largest, and then you split it in half, and then you split the lower half in half. Now you've got quarters, right? And the upper half in half, more quarters, right? And so now you've split your data into quarters, right? So let's say you've got the minimum to the maximum value here, and then you've got your median in the middle, and then splitting it into quartiles, I've got Q1 and Q3. Nice try, Emily. Splits your data into quarters. Okay, why would we use this? We're going to focus on the distance between Q1 and Q3, which is the distance between the central 50% of the data, right? I've got 25% of the data here, 25%, 25%, 25%, and 25%. Okay. And so if we are talking about especially a skewed distribution, right, then I've got outliers. I can find the quartiles for a normal distribution, but it's kind of boring, right? And so I would use the quartiles for a non-normal distribution. So now what I do is I can lob off these outside quarters, and I can focus on this interquartile range. And that's going to be my measure of spread for a non-normal distribution, right? I've lobbed off those kind of outlier points, and now I'm just focusing on the range between Q1 and Q3. So the interquartile range is abbreviated IQR. And it's going to be Q3 minus Q1, just because you want to have a positive range, right? If you find Q1 minus Q3, you'd get a negative because Q1 is always less than Q3. But that's okay. Right now we find a positive distance, and that's going to be our measure of spread for non-normal data. The IQR, the interquartile range, right, the distance between quartiles, the IQR, which is, I'll summarize it here, Q3 minus Q1, will be our measure of spread for non-normal data. We can use it for normal data, right? But then we have kind of more powerful tools in the variance and the standard deviation, right? And so then we should be using those instead, okay? But not the other way around, right? We shouldn't be using the standard deviation for non-normal data, right? And maybe I'll highlight this part as well. Good. So, okay. So now we've got the shapes, we've got the center, we've got the spread for normal and non-normal distributions. And so kind of the next step is to be able to identify outliers, right? So we can look at a distribution and it might look something, do I have an example in here? I don't know. Let's see. Might look something, none of them have outliers, but it might look something like this, right? And I don't suspect that any of these are outliers, but let me just grab one and make one. Right. Okay. So if I extend this and I put a fake data point out here, or maybe a couple tall, doesn't matter, all right? Just adding it to this distribution. So now we have a suspected outlier. Okay, so a suspected outlier in our data. That's not usually good enough, right? If we say, oh, and then I suspect that this is an outlier, then someone can come back to you and say, well, is it an outlier or not? Right? And so then we need, what? Hello? Oh. Hello? I'm just in case. If you had a question, Conrad, then you can ask, but I feel like maybe not. Seems like. I just go by the name showing up. Oh, someone's just crashing the. What a way to spend a month.
On the water side anyways, I don't know about the others, but.
I'm here.
You're here in this class.
Yeah.
Sounds good. Did you have a question?
No, for now.
Okay, sounds good. That settles that then. No worries. Okay, so we need to be able to say, well, is it an outlier or not? And then what's the follow-up? If you have an outlier in your data, what are you going to do with it? Right, and so that would be the follow-up, or how did it get there? Right, is it interesting? Is it a data entry thing? And so it kind of evolves, I guess. So one of the ways that we can determine if we have an outlier, throw myself off, is I jumped ahead. Sorry, guys, got too excited. I wanted to talk about outliers, so I will. This isn't very helpful, but I'm throwing it in there to introduce it. This is what I wanted. So one of the kind of old school ways of identifying outliers is called the 1.5 IQR rule. And so we can identify outliers by the 1.5 IQR rule. Now, what the 1.5 IQR rule says, okay, so we recognize that IQR, which is the interquartile range. And then what the rule says is that, okay, so you've got some distance between your quartiles here, right? And so what we can do is we can multiply that by 1.5. Now, 1.5 is completely arbitrary, but it's what's been settled on. Tukey suggested it, this famous statistician, and so he kind of led the way, but there's lots of different ways that you could do. You could do 2 times the interquartile range, or I don't know, 1.75, I'm sure is floating around, but traditionally we just use 1.5 times the interquartile range. And so what we're saying is that, okay, I'm allowed to go 1.5 times the interquartile range down from Q1 Okay. Anything past that point is going to be considered an outlier, or up from Q3, right? Because I want to find bounds from some starting points, and then anything beyond that is going to be considered an outlier. And so, let's see here. Put it down here. The 1.5 IQR rule says that we're going to have some lower bound, which is going to be Q1 minus 1.5 times the interquartile range. I'll highlight the minus because I want to move down from Q1, right? Q1 and Q3 are considered kind of robust measurements, right? And then the tail areas, well, anything can happen there. Whereas Q3 going up from Q3 gives us the upper bound, Q3 plus 1.5 times the interquartile range.
After doing this, we get like Q1 and Q3.
Well, you would have Q1 and Q3 because the interquartile range is Q3 minus Q1. So you already have those, but what you can do is you can move down from Q1 and then up from Q3. Does that make sense?
Yeah, but once you, if you've gotten rid of the outliers,
So
you have to recalculate some stuff.
yeah, so we're just trying to identify outliers right now, right? To say, hey, you're an outlier because, and we need that because part, because you're outside these lower or upper bounds, right? We can have outliers on the lower end, we can have outliers on the upper end. And so any values in the data beyond these bounds I guess I'll put a bracket around the values. In the data beyond these bounds is considered an outlier. And so if you have a data set, especially a small data set, then you could sort your data and you could look at it. But usually we'll just use Excel, which means you're going to have your quartiles, and then you can move up and down your quartiles, and you can easily sort your data and figure out what is considered an outlier. To visualize it, we can use a box plot. Now, a box plot is just a visual summary. Copy. Of this calculation. So a box plot looks like this. Well, it has a box in the middle. So we've looked at histograms for the distributions, right, to look at the shape. And you could figure out the shape of this distribution by looking at the box plot, knowing that the anatomy of it. And so we'll start here with, well, you've got the median in the center. Right? And then we've got the boxes drawn around Q1 and Q3, right? Showing me the interquartile range. And then what we're going to do is we're going to find what are called whiskers, which is kind of cute. And so what happens is you draw your whisker, and often a whisker is drawn like this, but could look like this. I'll draw it like this. So what happens is you're only going to draw actual data points, but you found these upper and lower bounds. So let's say you found your upper bound is here, and maybe your lower bound is here. Right? You took 1.5 times the interquartile range, subtracted it from Q1 to find the lower bound, and then what happens is, well, there were no data points past this lower bound. So then where I draw my whisker to is just to the minimum value. Yeah. So this here is the minimum value. Whereas here, what color have I? Sure, I'll use red, root. To indicate that I have a value past the upper bound, I'm going to use a star or a dot, depending on what software you're using, right? And so what happens is we drew our upper bound kind of theoretically, and then we draw the whisker to the lowest data point within the upper bound, and then it indicates that there are outliers by just dots or stars or whatever. And so box plots highlight outliers as identified by the 1.5 IQR rule. So you could do all that work, but if you make a box plot, it'll just show it to you. Might be nice to be able to confirm it though. Kind of a more modern way of finding outliers is by standardizing values. So Z-scores are used quite commonly. Let's see here. So a Z-score measures how far an observation is from the mean, right? That's a deviation. We've seen that before. But what we want to talk about specifically is how many standard deviations from the mean is this value, right? And so a Z-score, and maybe it's here, Z-scores are a measure of how many standard deviations a value is from the mean. So Z, right, we can calculate Z scores for each observation in our data set, right? Because I've got Xi minus X bar, right? That takes us back to the deviations. And then I can divide by S to see how many sample standard deviations it is away from the mean. Yeah. And the reason we do that is because now, right, I could have some mean on some scale, some large scale, and some standard deviation. But what we can do is if I figure out how many standard deviations, right, a point is from a mean, then the scale all of a sudden doesn't matter. Now we're talking about now how many standard deviations away from the mean are you, right? Z-scores are typically used for normal distributions. Can use them for non-normal, but we'll just focus on normal. They're going to be centered on the mean, right? And so if I find some data point Xi minus X bar divided by S, this is going to be negative, right? All these points of, so here I've got my Xi on this number line here, right? If I let the mean be 4, for example, and on a number line I have 2 here, let's say, I'll bump that up. maybe here's a 2. 2 is, and let S be 1, just for simplicity, because I don't want to divide by anything. I want to divide by 1, rather. If I take the deviation, right, 2 minus 4, then I get -2 divided by 1. Well, then it's 2 standard deviations below the mean, and the below is indicated by Z for 2 is going to be 2 minus 4 divided by 1, which gives me -2, right? And this negative indicates below the mean. Whereas on the flip side here, if I have an observation of, I don't know, 5, maybe I'll do something more fun. 7, whoa. Then Z for 7 is going to be 7 minus 4 divided by 1. I'll go across, which is going to be 3, +3, which indicates that it's above the mean. So 3 standard deviations above the mean. Now, as a rule, in fact, it's called the empirical rule, what we're going to find is that the central 68% of the data is captured between the first standard deviations on either side of the mean. So that's kind of a useful thing, and I'll show you why. Or I'll try to, if I can copy this. So the empirical rule says that approximately 68% of the data is going to be within 1 standard deviation of the mean. What does that look like? Well, it looks something like this. If I have my mean here, then I'm going to have a Z equal to -1 and a Z equal to 1, right? So 1 standard deviation below the mean and 1 standard deviation above the mean. So if I trace this up, then what happens is that this area, right, which would be bars in our histogram, for example, right, then we've got approximately 68% of the data is within 1 standard deviation on either side. Okay. That's going to be useful because the area under the curve is a probability. This is useful because the area under the curve is a probability. So what does that mean? It means the probability of being within 1 standard deviation of the mean is roughly 68% or 0.68. So therefore, the probability of an observation within 1 standard deviation of the mean is approximately 68%. Should clean that up, 68. Same idea. If we move out 2 standard deviations on either side of the mean, then we've covered roughly 95% of the data. So that's a lot of the data, right? And by the time we move out to 3 standard deviations, then we've covered almost all. In fact, just as a rule, 99.7% is almost all the data. Just been established, but almost all is 99.7% of the data is going to be within 3 standard deviations. So then another way that you could identify outliers is if it's more than 3 standard deviations away from the mean, then it's an outlier. But we'll pick up there because I can tell I'm out of time. If you have any questions, let me know. Otherwise, see you Wednesday. Stop this.